So for the last several lectures, we've been looking at solutions, what happens when you mix solutions, and the basic reactions that take place in solutions, as well as how information dealing with solution can tell us the number of moles of material present in those solutions. And we introduced this idea of molarity, concentration, and other concentration units that can be converted into molarity, and using the molarity to as a way of counting atoms within the solution. So now we're going to change gears. We're going to move out of the solution phase and into the gas phase, and this is discussion of gas laws. So gases are one of the three main phases of matter, the other being the liquid and solid phase. And what's interesting about gases compared to the other two phases is that we can observe them and see a number of different properties. We can infer a lot of information from. So one thing that happens is they assume the shape and volume of whatever the container they're placed in. So if you put them in a little container, you can actually expand that container and the gas will expand to fill it. Water, on the other hand, does not. All right? Gases are very compressible. If you take that same gas, you can squeeze it down to a much finer volume. Liquids and solids, far less compressible. In fact, this is why your brakes work, your hydraulic brakes, is because there's a fluid in there that when you press on the master cylinder, it presses on the solution. If you get air in there, on the other hand, you compress the gas and your brakes don't work. So that fact that they're very compressible is good or bad, depending on the situation. Another property is that gases mix very evenly. And so it allows for rapid reaction. One of the benefits of solutions was that mixing is quite easy, and in gases the mixing is even greater. In fact, if I splash on some cologne and I walk into the classroom, you can smell me all the way to the other side of the room, hopefully the cologne. And this is due to the fact that the gas molecules of the perfume or cologne are able to travel all the way across the room very quickly. And lastly, gases have a much, much lower density than liquids and solids. As it turns out, you can actually classify and describe the behavior of gases based upon three major quantities, three major, mostly extrinsic properties. The first of which is the temperature of the gas. Volume is often a capital V, and temperature is often a capital T. And so these three quantities are useful in describing the nature of a gas, pressure, volume, and temperature together. Occasionally we will also use moles, which is given the symbol N in this discussion, and that is always delivered representing the number of moles of gas. And so we can use the number of moles of gas to relate to each of these quantities: pressure, volume, and temperature. Now, it turns out that these quantities are not independent of one another, and so we can change one set of these variables and it alters the other one. So early to late 1800s, scientists were working with gases, started to tease out these relationships between pressure, volume, and temperature, and recognizing that the quantities associated with each of these are related. So what is pressure? Turns out that pressure, gas, if we think of gas as individual molecules, and these molecules are moving quite fast, they're zipping around on the inside of a container, and those molecules smack up against the side of the container and bounce back. Those gas molecules exert a noticeable force on the surface of the container. And we can relate this force to the area of the container, and we can develop this idea of pressure, which is force per unit area. So force per unit area. The SI unit for pressure is the Pascal, which is composed of two other SI units, the Newton and the meter. So a Pascal is 1 Newton per meter squared, which is actually a very, very small quantity, and it's less than the force of a piece of paper on a desk. The force of this piece of paper on my hand is about 1 Newton per meter squared. It's not much. Right? So pascals are very small. A more convenient unit for pressure, though, is the atmosphere. It turns out that, just like this paper pressing down on my hand, we, at the bottom of our gravity well, this is me, Dr. Dan there, you can tell it's me because I'm holding a coffee cup. We are at the bottom of 20 miles of air. So we are at the bottom of a pile of anywhere between 20 and 30 miles of air, depending on how you draw the line. And even though air is very light, it still has mass. And above us is this column of air, 20 miles tall, pushing down on us. And the weight of that air exerts a pressure on us. And so we have defined a standard unit for pressure as an atmosphere. It's the approximate weight. It's the approximate weight of the atmosphere on us at that given time. And it's given the abbreviation ATM. And it turns out that 1 atmosphere is about 100,000 pascals, or 101 kilopascals. And so this weight of air has defined as a standard unit. We don't really notice it. We walk around in it. We've evolved into it. So it's not a huge impact on our daily life. So we are not overly aware of its presence. But it exists all around us. For a balloon to maintain its pressure, its shape, it has to exert a force on that balloon at least equal to the atmospheric pressure. So when we take a container and we fill it full of air or other gas and we seal it, it's at 1 atmosphere. And if the weather changes or you move that bottle to an area of higher or lower pressure, you can actually see the bottle deform. Even driving down to a slightly lower elevation, you can actually see the bottle compress due to the pressure of the air pressing in on the lower pressure. So this is an atmosphere. Now, we can measure these pressures a number of different ways. One of the easiest ways is to use to measure atmospheric pressure, or the air, the pressure inside of say a room or something. We often use what we call a barometer. And in this case, in a barometer's case, it's usually a upended tube of mercury that sits in a pool of mercury. Now, mercury is a liquid, it flows quite readily, but if you fill a glass tube filled with mercury, and the tube is long enough, and you fill it completely up, and then you upend it into mercury, the mercury will sag and create a small partial vacuum above the mercury. Effectively, this is a vacuum above the mercury. And the reason it just doesn't drain out, though, is because the weight of the atmosphere pushes back up against it. Pushes it back up the column. Now, you can actually do this with water and do the same thing with water, but air, the atmospheric pressure, will actually support a huge column of water. Actually, one of the problems in your book deals with this, so I'm not going to spoil it for you. But there's this thing called the internet, and you can probably find it out pretty quick, how high that column of water would actually be. Fill up this cup with water, and then you take it under, plunk it down in a tub of water, and turn it over, and lift it out. The water inside the cup will not fall out. The water would fill up the cup. This entire column would be filled with water. Why? Because the air pressure is pushing the water up, preventing it from draining out. Now, the only way you could drain the water out is if you could fill the space above it with air, which is not a problem if you have a leak. So that's a barometer. But a barometer only works with measuring bulk atmospheric pressure or external pressure. And as it turns out, the average height at sea level for this column of mercury turns out to be 760 millimeters of mercury high. And so we can use the measurement of the height of the mercury as a measure of atmospheric pressure. And then this is often also described as a torr. So 760 torr is equal to 760 millimeters of mercury, which is equal to 1 atmosphere. All right, so all of these are exact units. One of the issues when dealing with gas law problems is converting between these. You should know millimeters of mercury to atmospheres because it's quite common. You will probably be provided atmospheres to kilopascals or pascals. Even though the SI unit is pascals, we often rely very heavily on millimeters of mercury and atmospheric pressure. So that is measurement of pressure in the bulk setting. Now, what about in the lab? In the lab, we use, rather than a barometer, we'll use one of two different things. We'll use what we call a manometer, a manometer. It's a manometer. I can't use a manometer. The manometer keeps going off the scale, which is similar to a barometer, except it is also filled with mercury. And the difference in the height between the two columns would represent, in a closed system, would represent the pressure inside the container in millimeters of mercury. And so the height difference between the inside and the lower would represent, this would if this was 23 millimeters of mercury high, this would represent that the pressure inside the flask that it was connected to would be exerting a positive 23 millimeters of mercury pressure. Now, similar to this is the open manometer, though, where rather than being a sealed glass tube, would have a open junction. And like in our previous example, it would also be filled with mercury, and the difference between these two units would represent the difference in the pressure between external and internal. We don't often use manometers in the real world, except when you're dealing with gases specifically. And so this pressure difference, if the loop associated with the external pressure was higher than the internal, that would represent that the internal gas has more pressure associated than the external by the difference. What it means is the gas inside is pushing out. If you ever blown into a straw, you know how the manometer works. By exerting a positive pressure, you're displacing the water from the tube. By exerting a positive pressure, you're displacing the mercury from the tube. But in this case, the mercury, the liquid, is being sucked back up into the tube, so it's a negative pressure. And so what this means is if atmospheric pressure was 760, this 10 millimeters of mercury would represent the difference. In this case, a negative 10 millimeters of mercury towards the gas. So the gas pressure would be 10 millimeters of mercury less than the external pressure. In this case, it was 1 atmosphere, it'd be 750. So the difference would represent that. So from that height difference, either pushed back against by the external pressure. And so we can use these very simple apparatus to measure the pressure of a container. You can also use various gauges to do the same thing, right? But they often rely on the same, the gas pressing up against some sort of calibrated disc. So that's pressure. Pressure, the force the gas exerts on the system. Now, before we get too crazy, let's continue on and talk a little bit about the temperature. It turns out that one of the early recognized relationships in gases had to do with the volume and the temperature. As it turns out, something that if you've ever carried balloons around in the middle of winter, you know that the volume is related to the temperature of the gas. And so the volume is related to the temperature of the gas. Now, this is what we call Charles' law. It turns out that for any given gas, the temperature of the gas and the volume of the gas are proportional. So you can relate, one way of saying this mathematically is that the volume and the temperature are related via the constant. A volume is equal to a constant times T. Typically, though, as the temperature increases, the volume increases. This is why bread rises. We put that loaf of bread in the oven, it puffs up because of the temperature increase in the gas in the bread, more so than sudden activation of the yeast or anything like that. So the gas bubbles swell up due to their increase in temperature. Now, there's a hidden little bit of information in here, and if you take a look at the temperature and you just slowly increase the temperature, and then you observe the volume as a function of temperature, you'll see that the volume goes up in a regular fashion. And this is a 0 degrees centigrade. This was say 100 degrees centigrade, the boiling point. But what that means is that the corollary is true. As you decrease the temperature, the volume will go down too, until at some point the volume will become 0. It's not like you can make a negative volume. You can't have something that takes up less space than it has. What this implies is that there is some bottom temperature. Well, that temperature is what we call absolute zero. For us, that's about minus 273.15 degrees centigrade. So rather than talk in degrees centigrade, we fix the zero such that we choose the zero of our new scale to be minus 273.15 degrees centigrade. That's what we call absolute zero, or 0 Kelvin. So we can create a new scale where rather than the freezing point of water being 0 degrees C, the freezing point of water is 273.15 Kelvin. And just for the sake of correctness, it's Kelvin, not degrees Kelvin, because it's an absolute scale. So we call this absolute scale, or absolute temperature scale. And the absolute temperature scale is based upon the Kelvin. As it turns out, though, that a change of 1 degree centigrade has the same magnitude as a change of 1 degree Kelvin. And so we can relate the two quite easily between that. Between the two, 273.15 plus degrees centigrade will equal Kelvin, and vice versa. And so we can relate Kelvin and centigrade quite easily. When you're working with gases, you should almost always be in Kelvin. This will save you much gray hair later. So, you should always be in the absolute scale. All right? So, pressure and temperature. This relationship between volume and temperature we call Charles' law. So if we use an absolute scale, what that means is that given any two volumes and temperature, temperatures, if volume is equal to K2T, that given any two temperatures, the same gas at a different temperature will have a different volume, but those will have the same, they can be related via this constant. So we can rearrange and combine these two equations to get the following. V1 divided by T1 is equal to V2 divided by T2. All right, this is what we call Charles' law. Charles' law allows us to relate temperature and volume given any two sets of conditions, as long as we keep in mind that this is absolute temperature, or Kelvin. So we've introduced the first of our gas laws, the Charles' law. As it turns out, there's 3 or 4 other gas laws, and then another one on top of that. So how do we keep track of all these gas laws, and how do we be sure to ensure that we are successful? Well, as it turns out, there's a couple things you can keep in mind that maximize your chances. The first is units. Surprise. It's like the only thing we've been talking about. Be sure that all your units are the same. All right, if you're dealing with temperatures, make sure you're dealing with temperatures that are in the same set of units. Dealing with pressures, make sure that everything is related to a comfortable unit. Atmospheres is really often the most successful. All right, so it's helpful to convert everything into atmospheres. Another thing is, look at the problem. Look for key words like change or things that stay the same. A general tip is start lifting out starting conditions and ending conditions. You should keep track of the 4 major quantities: pressure, volume, temperature, and the moles. Oftentimes you'll see 2 or 3. How can there be 2 pressures in this problem? Well, it turns out that maybe something is changing. So that's what the next question you're going to ask yourself. Is something changing over the course of the problem? Or is it asking you to find something that's missing? All right. Those are really the most common types of gas law problems. And another thing to keep in mind is that if something is not explicitly mentioned, it might mean that it's not changing. And so we can often hold things steady. Like, you can have a bunch of gas law problems that don't talk about the moles of gas. They might not even consider the identity of the gas. And so do we have to find the number of moles? Oh no, the moles isn't listed. Well, maybe we don't use it. So, and lastly, there's this idea of STP. Oftentimes you'll see it shorthand notation. STP stands for standard temperature and pressure. It turns out that what that really means for you is a standard temperature and pressure of 1 atmosphere and a temperature of 0 degrees centigrade, or 273.15 Kelvin. That's standard temperature and the pressure. Standard temperature pressure. The reason why it's standard is we exist at 1 atmosphere, so we can very easily capture 1 atmosphere of gas. And it's very easy to make that gas at 0 degrees centigrade. You just plop it down into an ice bath. 2 very convenient methods of dealing with gases. So standard temperature and pressure means 1 atmosphere is 0 degrees centigrade. So if you see that, you might not see a pressure or volume, pressure or temperature listed. You just have to know that STP represents 1 atmosphere and 0 degrees centigrade.